The sky itself was humanity's first clock. For thousands of years, our ancestors lived in a world without schedules. Their only guides the sun's arc and the moon's silent dance. This is the story of how we learned to measure time itself. You will finish this journey understanding the hidden code that connects ancient monuments to the watch on your wrist. We will uncover how a mysterious bronze disc held the key to the seasons, and why a 2,000-year-old shipwreck yielded a computer more complex than anything built for a millennium. How did civilizations with only stone and bronze achieve such staggering precision? By the end, you will see the rhythm of the cosmos through their eyes. What part of your own day would you sacrifice to live by the sun and stars alone? That Neolithic farmer staring at the sky was not just watching for weather. He was reading the only calendar his people had, a desperate search for the signal to plant seeds and ensure his family's survival. This was the primordial engine of timekeeping. The very rhythm of life and death was governed by celestial patterns. Knowing when the Nile would flood, when the caribou would migrate, or when the monsoon rains would arrive was not a matter of convenience. It was the difference between a thriving community and a forgotten one. This urgent, practical need drove the first great astronomical observations, but the human mind is never satisfied with mere survival. As these societies grew more stable, their relationship with time deepened. They began to see patterns everywhere. They noticed that the sun did not just rise and set randomly. It traveled along a predictable path throughout the year, rising and setting at different points on the horizon. The moon cycled through its phases with a reliable regularity that could mark periods longer than a single day. Even the stars, which seemed fixed, slowly wheeled across the night sky in an annual dance. This was the birth of true timekeeping. It was an attempt to impose human order on the cosmos, to translate the silent, mechanical movements of the heavens into a language their communities could understand and use. This was more than science. It was a philosophical and spiritual quest. By understanding time, they believed they could understand the intentions of their gods, the cycle of rebirth, and humanity's own purpose within the grand scheme of existence. This foundational urge, born from the soil and raised to the stars, set the stage for inventions so precise they would baffle us for centuries. How do you build a calendar from stone and shadow? The sun and moon were the original architects of our calendar. That fiery disk rising in the east and setting in the west gave us the day, the most immediate pulse of time. But ancient sky watchers noticed something more. The sun's rising point was not fixed. It crept along the horizon, traveling north as the world warmed into summer, then sliding south as the cold returned. This slow, annual dance marked the seasons, a rhythm as vital to a farmer as his own heartbeat. Alongside the sun, the moon offered its own silver measure. Its cycle from slender crescent to glowing full disk and back again gave humanity the month, a shorter, more poetic unit of time. People counted these lunar cycles and saw that roughly 12 of them fit within the sun's yearly journey. But it was not a perfect fit. This slight mismatch, this stubborn fractional day left over each year, became one of history's great chronological puzzles. How do you build a calendar that reconciles the sun and the moon? The challenge was immense. To track these cycles with greater precision, ancient astronomers identified pivotal moments in the sun's journey. The solstices, the year's longest and shortest days, when the sun seemed to stand still at the limits of its path, and the equinoxes, those two perfect balances each year when light and darkness held equal dominion over the earth. These were not merely abstract astronomical events. They were woven into the spiritual and cultural life of every early society. The winter solstice might signal a festival of rebirth, a celebration that the sun was returning. The spring equinox could mark a time of planting and renewal. Time was not just measured, it was felt and celebrated, a sacred cycle that connected the community to the cosmos. This deep, celestial dependency could not rely on memory alone. It demanded something permanent, something stone and earth could provide. The human answer was to build clocks on a monumental scale. These stones did not simply mark a single day. The entire arrangement functioned as a celestial computer carved from earth and rock. Beyond the dramatic solstice sunrise, the monument's other alignments whisper of deeper knowledge. The 56 Aubrey holes encircling the structure may have been used to track the moon's more complex 19-year cycle, a cycle that includes eclipses. Imagine the power this knowledge held. By moving a marker from hole to hole each year, a keeper of time could predict when the moon would turn to blood or the sun would vanish from the sky. In an age without writing, this was more than a calendar. It was a sacred machine for foreseeing the gods' most dramatic acts, a way to assert human order over cosmic chaos. This was a communal effort on a staggering scale, requiring generations of labor to align multi-ton stones with the sky's slow rhythms. The true purpose of Stonehenge was not just to observe the heavens, but to anchor time itself to the British landscape, creating a permanent, unshakable link between the people and the cosmos they revered. This monumental ambition was not unique to the misty hills of England. On the other side of the world, another civilization was solving the same problem with a different, yet equally brilliant stone solution. Far from the standing stones of Britain, a different kind of timekeeper was buried in the dark soil of Germany. The Nebra Sky Disk is not a monument you can walk through, but a handheld map of the heavens cast in bronze and gold. Crafted over 3,600 years ago, it is the oldest known realistic portrait of the night sky. Against a deep blue-green patina, golden symbols shimmer. A full sun and a crescent moon share the space with a precise cluster of 7 stars, almost certainly the Pleiades. This was more than sacred jewelry. It was a sophisticated instrument for harmonizing the conflicting rhythms of the sun and moon. The appearance of the Pleiades at certain times of the year was a critical signal for farmers across the ancient world, a celestial alarm clock for planting and harvest. But the disk's genius lies in its ability to bridge timekeeping systems. By observing the moon's phases against the backdrop of this specific star cluster, a Bronze Age person could know when to add an extra, or intercalary, month to keep their lunar calendar in step with the solar year. This prevented their seasons from slowly drifting into chaos. Along the disk's edge, 2 golden arcs were later added. Researchers believe these mark the exact angle between the rising and setting sun at the solstices, capturing the sun's yearly journey in a span of metal you could hold in your hands. This portable technology reveals something profound. Astronomical knowledge was not locked away in stone temples for a privileged few. It was practical, widespread information carried by individuals, a farmer's almanac and a priest's ritual object fused into one breathtaking artifact. It proves that the desire to measure time accurately, to hold a piece of the cosmos in your hand, was a need felt across entire continents. This drive for precision would soon demand mechanisms far more complex than a static disk could provide. That handheld bronze disk was a map of the cosmos, but it could not divide a single day into manageable hours. The solution to that problem would not be found in the stars, but in the slow sweep of a shadow across the ground. The first sundials were not intricate devices but simple obelisks, their long shadows tracing a silent arc from dawn to dusk. This was the birth of the hour, a division of daylight itself. The Egyptians refined this concept around 1500 BCE, creating T-shaped bars that cast a more defined shadow, marking time in clearer intervals. But it was the Greeks and Romans who transformed the sundial from a public monument into a personal possession. They crafted portable dials, often from bronze or even ivory, that were marvels of geometry. These were not simple sticks in the ground. Their curved scales were carefully calculated to account for the user's latitude and the sun's changing path through the seasons, correcting for the fact that an hour in the summer was longer than an hour in the winter. To read one correctly was to understand the Earth's tilt and its journey around the sun. A sundial was more than a clock. It was a personal, physical link to the solar cycle, a constant memento that the day was fleeting. The Roman writer Pliny the Elder observed that a sundial could remind a person to reflect on how they spent their own life, as the shadow moved relentlessly forward. This evolution from massive stone circles to a device you could carry in your pocket marked a profound shift. Time was no longer just a communal rhythm observed by priests or kings. It was becoming a personal responsibility, a measure of one's own daily actions. Yet for all their elegance, sundials shared one fundamental weakness. They were useless on a cloudy day and utterly silent in the deep of night. The cosmos offered another timekeeper, one whose cool, constant light governed the darkness. While the sun measured the day, the moon offered a different kind of time. Its silent, silver transformation from a slender crescent to a glowing orb and back again gave humanity the month, a rhythm deeply woven into our earliest calendars. This consistent 29-and-a-half-day cycle was a powerful, visible heartbeat in the night sky. Many of the world's first civilizations, from the astronomers of Mesopotamia to the scholars of ancient China, structured their years around these lunar months. Each new month began not with a date on a page, but with a collective vigil, watching for the first faint sighting of the new crescent moon. This created a year of roughly 354 days. But here lay the great challenge. This lunar year was 11 days shorter than the solar year. Imagine celebrating a spring festival, only to find that a few years later, it was falling in the dead of winter. The seasons, dictated by the sun, were slowly drifting out of sync with the moon's sacred rhythm. To solve this, societies developed a brilliant fix called intercalation. This was the periodic insertion of an extra month into the year. The Babylonians became masters of this, carefully observing the skies and decreeing when a 13th month was needed to pull their lunar calendar back into alignment with the agricultural and ceremonial seasons. This was not just an administrative task, it was an act of cosmic balancing, a way to keep their harvest festivals and religious rites anchored in their proper time. This struggle to reconcile the moon and the sun pushed ancient astronomers to new heights of mathematical sophistication. But beyond the math, the lunar calendar was a cultural force. It governed everything from market days and legal proceedings to the most sacred religious observances. The Islamic Hijri calendar, still in use today, remains a purely lunar system, its months cycling through the solar seasons over a 33-year period. The moon's visible cycle provided an intuitive metaphor for life itself, a constant reminder of birth, death, and rebirth that resonated in mythologies across the globe. Yet this celestial dance between the sun and moon was a problem that demanded more than just observation. It required a machine. The ancient Egyptians faced a problem far greater than any philosophical puzzle. Their entire civilization, nestled along the fertile banks of the Nile, depended on the river's annual flood. Predicting this life-giving event was a matter of survival, and they found their answer not in the river itself, but in the pre-dawn sky. Each year, just before the sun rose, the brilliant star Sirius would reappear after a 70-day absence. This heliacal rising was their celestial alarm clock, its first gleam perfectly heralding the Nile's imminent inundation. This moment was so profound it marked their New Year's Day, weaving the rhythm of the cosmos directly into the pulse of the Earth. From this perfect alignment of star, river, and season, they engineered one of history's most influential inventions, a 365-day civil calendar. They divided the year into 12 clean months of 30 days each, but they recognized the cosmos demanded a little more. They added 5 extra days at the year's end, sacred days dedicated to their most powerful gods. This was a monumental leap, a primarily solar-based system that abandoned the messy struggle to synchronize with the moon. For the first time, a society had a stable, predictable framework for organizing everything from planting and harvest to religious festivals and tax collection. Yet this brilliant system contained a tiny, almost invisible flaw. Their calendar ignored the quarter day it actually takes the Earth to orbit the Sun. Without a leap year, their New Year's Day crept forward one day every 4 years, silently drifting through the seasons. This slow dance was so gradual it took 1,460 years for their calendar to realign perfectly with the Sirius rise, a grand cycle later known as the Sothic cycle. This elegant, practical calendar became the administrative backbone of an empire that lasted for millennia, a testament to their masterful fusion of astronomy, environment, and faith. It was a tool of such power and accuracy that its basic structure would echo through the ages, influencing the very calendar you use today. But what happens when this knowledge of time needs to travel, when you cannot wait for a star to rise or a shadow to move? The next chapter of timekeeping would be found not under the open sky, but deep within a 2,000-year-old shipwreck at the bottom of the sea. The sea held its secret for 2,000 years. In 1901, sponge divers exploring a Roman-era shipwreck off the coast of the Greek island of Antikythera stumbled upon a corroded lump of bronze and wood. Initially overlooked amidst statues and pottery, this unassuming object would later be recognized as the most technologically complex artifact to survive from the ancient world. We now know it as the Antikythera Mechanism. This was not a simple timekeeper. It was a portable cosmos, an intricate analog computer built from at least 30 interlocking bronze gears, all housed in a wooden case no larger than a shoebox. Its purpose was not to count hours, but to simulate the very movements of the heavens. Crafted around the 2nd century before the Common Era, its complexity would not be matched for over 1,000 years. By turning a small hand crank on its side, a user could advance the mechanism day by day, year by year. As the gears turned, a series of dials on the front and back would move, displaying the predicted positions of the Sun, the Moon, and the 5 known planets. It could show the phases of the Moon and, most astonishingly, predict lunar and solar eclipses decades in advance. This was a machine that calculated time across multiple, overlapping cycles simultaneously. One of its dials tracked the Metonic cycle, a period of 19 solar years that equals exactly 235 lunar months. This was the very same cycle the builders of Stonehenge may have tracked with their Aubrey holes, but here it was automated, calculated by the precise turn of a gear. Another dial accounted for the Callippic cycle, a refinement that made the Metonic cycle even more accurate over longer periods. The mechanism even incorporated a complex set of gears to model the Moon's irregular orbit, a subtle wobble known as lunar anomaly. This meant the device did not just show the Moon's position, but its varying speed across the sky, a level of astronomical sophistication that is breathtaking. This single device represents the ultimate fusion of all the ancient world's timekeeping knowledge. It brought together the solar year, the lunar month, and the planetary cycles into one unified mechanical simulation. The Antikythera Mechanism was more than a tool for priests or astronomers. It was a philosophical statement cast in bronze, a declaration that the cosmos operated by predictable, mechanical laws that the human mind could not only understand but replicate. Its existence shatters the myth of linear progress, revealing a brilliant peak of ancient science and engineering that was tragically lost to the depths for centuries. The brilliant gears of the Antikythera Mechanism represented a peak of ancient engineering, but its complexity was a rarity. For the everyday task of telling time after sunset, humanity turned to a more elemental force. Water itself became the measure. From the bustling courts of Athens to the silent temples of Egypt, the clepsydra, or water clock, transformed the night into something that could be counted. The simplest form was a humble bowl with a small hole drilled in its base. Placed in a larger vessel of water, it would slowly fill and then sink after a precise interval, a single, audible gulp marking the passage of a period. This was time made tangible, not by a moving shadow, but by a steady, liquid flow. The need for this technology was urgent and practical. In ancient Greek law courts, a water clock would be filled to a specific level to time a speaker's argument, ensuring fairness and preventing endless debate. The drip of water was the sound of justice in action. Armies used larger, more robust clepsydra to regiment the night watch, dividing the long, dark hours into manageable, equal shifts. And in temples where rituals had to be performed at exact moments regardless of the sun's position, the regulated flow of water provided a sacred rhythm for the night. The evolution of these devices was a march toward greater precision. Simple sinking bowls gave way to elaborate systems of multiple containers. In one advanced design, water dripped from a central reservoir into a receiving vessel. As the water level rose, a float would lift, and this motion was connected to a gear train that could move a pointer across a dial, or even trigger bells and moving figurines. This was the direct mechanical ancestor of the weight-driven clocks that would emerge centuries later. The core innovation was profound. For the first time, humanity was measuring uniform intervals of time that were independent of the cosmos. An hour from a water clock was a fixed amount of water, not a variable length of daylight. This was the crucial mental leap from observing time to creating it, abstracting its flow from the natural world and containing it within a human-made system. Yet this new power had its limits. Water is susceptible to the world around it. On a cold night, it could freeze. On a hot day, its viscosity would change, altering the flow rate. Mineral deposits could slowly clog the carefully calibrated holes. The clocks were also slaves to water pressure, as the flow would slow slightly as the main reservoir emptied. These were the stubborn physical problems that inventors would grapple with for generations. Despite these imperfections, the water clock was a monumental shift. It moved timekeeping from the cosmic scale of Stonehenge and the Nebra Disk to the mechanical and the personal. It enabled the night to be organized, studied, and utilized. This relentless pursuit of a constant, reliable beat, a rhythm untethered from the stars, would eventually demand a new kind of power, one that pulsed with a life of its own. The steady drip of water was a sound of order, but it was not the only rhythm humanity found. In the quiet halls of East Asian temples and palaces, time was measured not by sight or sound, but by scent. Incense clocks transformed the very air into a clock. Carefully crafted sticks or intricate coils of incense were designed to burn at a perfectly consistent rate. Marks along their length indicated the passing of hours, while the specific fragrance of the incense could signal different times of day. A morning hour might be announced by the crisp aroma of pine, while an evening hour was marked by the deep, calming scent of sandalwood. This was timekeeping as an art form, a multi-sensory experience that engaged the spirit as much as the mind. It turned the abstract passage of time into an elegant, aromatic journey. Across the world, a different substance was falling. In medieval Europe, the hourglass harnessed the relentless flow of sand. Its design was a masterpiece of simplicity. Two glass bulbs connected by a narrow neck, it measured a fixed interval as fine sand poured from the upper chamber to the lower. Unlike the water clock, it was immune to freezing. Unlike the sundial, it worked in any weather, day or night. This reliability made it indispensable at sea, where navigators used it to calculate a ship's speed and to mark the half-hour watches that governed life aboard a vessel. On land, it timed a preacher's sermon, ensuring theological arguments did not overstay their welcome. It regimented shifts in early factories, its turn marking the beginning and end of a worker's labor. Both of these devices, the aromatic and the granular, shared a profound underlying principle. They measured time through the consistent, irreversible consumption of a material. The incense clock appealed to the soul, its fragrant smoke a poetic reminder of time's ethereal nature. The hourglass provided a stark, visual metaphor, a silent, physical demonstration of moments draining away. You could see your allotted time literally running out. These tools reveal a beautiful diversity in human ingenuity. Different cultures, with their unique materials and philosophies, arrived at distinct yet equally brilliant solutions to the same universal problem. They were measuring duration itself, creating pockets of predictable order from the chaos of flowing sand and rising smoke. Yet for all their cultural resonance, these methods still relied on the physical properties of the world, on substances that could clog, vary, or eventually be consumed. The next great leap in timekeeping would require something far more constant, a beat that nature itself could not disrupt. Deep within the jungles of Mesoamerica, the Maya constructed a vision of time so intricate it defies simple explanation. They did not see time as a straight line marching toward the future, but as a sacred wheel, a complex tapestry of interlocking cycles where the divine and the human were forever intertwined. At the heart of this system were two distinct calendars spinning in a perpetual, elegant dance. The first was the Tzolk'in, a 260-day sacred calendar. This was not a count of seasons, but a spiritual almanac. Each day was a unique combination of a number from 1 to 13 and one of 20 sacred day names, creating 260 distinct energies. This cycle governed rituals, divination, and the very fate of individuals and communities. A Maya priest would consult the Tzolk'in to determine the most auspicious day for a marriage, a coronation, or a battle, believing that the specific quality of that day would influence the outcome. Alongside this sacred wheel ran the Hob, a 365-day solar calendar more familiar to us, used for organizing agriculture, tracking the seasons, and civil affairs. It was divided into 18 months of 20 days each, with a final, unlucky period of 5 days to complete the year. These two calendars, the Tzolk'in and the Hob, spun independently. Imagine two gears of different sizes turning side by side. It took a full 52 years for a specific date on the sacred calendar to realign with the same date on the solar calendar. This grand cycle was known as the calendar round, and its completion was a moment of profound cosmic significance for the Maya, a time of renewal and potential upheaval when the world was thought to be in danger of dissolving back into chaos. But for recording the vast sweep of history, for anchoring their kings and their conquests in a timeline that stretched back to a mythical beginning, they needed something more. This was the purpose of the long count. This was a linear count of days from a fixed starting point, a day zero that scholars equate to August 11th, 3114 BCE in our calendar. The long count allowed them to inscribe a date on a temple stela with absolute precision, ensuring that the deeds of a king would be remembered for millennia. Their astronomical observations fed directly into this sacred mathematics. From their towering pyramid observatories, they calculated the solar year to be 365.2420 days, a figure astonishingly close to our modern calculation of 365.2422. They meticulously tracked the 584-day cycle of Venus, viewing its morning and evening appearances as the movements of a powerful and often malevolent god. Wars were sometimes timed to coincide with specific celestial events, a belief that the power of the stars could be harnessed for earthly conflict. For the Maya, this entire system was far more than a method of organization. Time itself was a divine force, a living entity composed of layers of sacred energy. Their calendars were not merely tools, but a way to decode the intentions of the gods and to find humanity's proper place within the endless, repeating rhythms of creation. This profound, cyclical world-view stands in stark contrast to another ancient tradition, one that sought to find a single, harmonious rhythm for all of humanity. Even the hour, that most basic unit of our day, was once a shape-shifting concept. The Egyptians, masters of solar observation, divided the period from dawn to dusk into 12 equal parts. This seems logical until you realize its profound implication. On the longest day of summer, each of those 12 daylight hours was vastly longer than each of the 12 hours of the short summer night. A daytime hour in June could last the equivalent of our modern 75 minutes, while a nighttime hour might be a brief 45. Their sundials were built for this reality, often featuring adjustable gnomons or multiple scales to account for the sun's changing path through the year. Time was still tethered directly to the sun's arc, a personal and local experience that stretched and contracted with the seasons. This system of temporal or unequal hours reflected the natural world's rhythm, but it was ill-suited for the demands of a complex, interconnected society. How could you schedule a meeting or pay a worker by the hour when the hour itself was never the same length from one week to the next? The solution required a radical abstraction of time itself. This leap was made by Greek astronomers who conceived of the equinoctial hour. They proposed dividing the entire day, not just the daylight, into 24 equal parts. This was a theoretical marvel, but a practical nightmare for sundial makers, as these equal hours rarely matched the uneven segments of sunlight. The idea only became truly practical with the rise of mechanical timekeepers, particularly sophisticated water clocks that could measure a consistent flow regardless of the season. The adoption of 24 equal hours was a quiet revolution. It severed time's direct link to the sun's position in your local sky and redefined it as a universal mathematical constant. An hour was now an hour everywhere and always, a fixed container for human activity. This was the essential foundation for everything that followed, from Newtonian physics to railway timetables. It allowed for the precise coordination of scientific experiments, the fair regulation of labor, and the intricate scheduling of urban life. The struggle to define something as seemingly simple as an hour reveals a deeper truth. Standardizing time was not a single event, but a slow, grinding process of convincing the entire world to agree on a single, artificial rhythm. And that agreement would soon face its greatest challenge as faster ships and trains began to compress the globe, revealing a chaos of local times that threatened to derail modern life itself. While Europe navigated by shifting sands and incense smoke, a civilization on the Indian subcontinent was contemplating time on a scale so vast it challenges our very perception of reality. Ancient Indian scholars conceived of time not as a line, but as an endless, breathing spiral of creation and dissolution. At the heart of this cosmology were the 4 yugas, immense ages of declining virtue that cycle endlessly. The Golden Satya Yuga, an era of truth and perfection, gives way to the Treta Yuga, then the Devapara Yuga, and finally our current age, the Kali Yuga, a time of conflict and spiritual darkness. But this is not the end. These 4 ages, with their precise, if symbolic, durations of thousands of divine years, combine to form a single Mahayuga, a cycle of over 4 million human years that repeats for all eternity. This was not merely myth, it was a philosophical framework that gave human life a context within the unimaginably long lifespan of the cosmos itself. How could one measure a single day when contemplating such immensity? The answer lay in a parallel tradition of breathtaking mathematical precision. In the 5th century of the Common Era, the astronomer Aryabhata calculated the length of the solar year as 365 days, 6 hours, 12 minutes, and 30 seconds. This figure is only a few minutes off from our modern value. He also proposed, centuries before Copernicus, that the Earth spins on its axis, explaining the apparent movement of the stars across the night sky. This was not guesswork. It was the result of sophisticated mathematical theories, including early forms of trigonometry and the use of simple yet powerful instruments. A tall gnomon or sundial pillar cast a shadow whose length and angle could be measured to determine the time of day and even the solstices. Water clocks, known as Gattaca, regulated the duration of rituals with a steady, liquid drip. This synthesis of the cosmic and the practical was essential to daily life. The complex Vedic rituals, which formed the bedrock of spiritual practice, had to be initiated at astronomically determined moments to be effective. A fire ceremony performed a few minutes too early or too late was believed to lose its power. Therefore, the village astronomer priest, the keeper of time, was a figure of immense importance. His ability to calculate the exact moment of sunrise or the precise position of the moon directly connected the community to the divine. In this system, measuring the passing of a single hour was not a mundane task. It was a sacred act that echoed the grand, rhythmic pulse of the universe, a way for humanity to participate consciously in the endless turning of the cosmic wheel. This profound connection between the infinitesimal and the infinite reveals a culture that saw no separation between the science of the heavens and the poetry of the soul. While Indian astronomers contemplated cosmic ages in the halls of Imperial China, timekeeping was a matter of state security. The emperor's right to rule, his very mandate from heaven, was proven by the perfect accuracy of his calendar. A single error in predicting a season or an eclipse was not a scientific mistake. It was a political catastrophe, a sign that heaven had withdrawn its favor, potentially sparking rebellion. This immense pressure fueled a state-sponsored scientific endeavor that lasted for millennia. At the heart of this system were the astronomical bureaus, elite institutions of scholar officials who observed the sky every night, generation after generation. Their mission was to create and maintain the official calendar, a document that governed everything from tax collection and planting schedules to the dates of all imperial ceremonies. This was not just a chart of days, it was the operating system of the entire civilization, a unisolar calendar of breathtaking complexity that harmonized the moon's cycles with the sun's year. To achieve this, Chinese astronomers invented some of the most sophisticated instruments the ancient world would ever see. They perfected the armillary sphere, a bronze model of the celestial sphere with rings that could be aligned to track the paths of the sun, moon, and planets across the sky. But one of their most revolutionary creations was a clock. In the 11th century, the engineer Su Song built a colossal water-driven astronomical clock tower over 30 feet tall. At its heart was a true escapement mechanism, a device that regulated the flow of power, turning a continuous flow into a steady, ticking motion. This was the mechanical heartbeat that would later drive all European clocks, but here it was in Kaifeng, centuries earlier, powering a celestial atlas that displayed the time and the movements of the stars simultaneously. The bureaus were also the world's most diligent archivists. They kept meticulous records of every irregularity in the heavens. Their logs noted guest stars, which we now know were supernova, appearing in the sky and then fading away. They documented comets with detailed descriptions of their tails and directions. They even recorded sunspots, viewing them through jade filters or by observing the sun's dim reflection in murky water. This created an unbroken chronicle of celestial events spanning over 1,500 years, a dataset so precise that modern astronomers still use it to study the long-term behavior of stars and our own sun. The entire system was a profound fusion of power, precision, and belief. The emperor, by issuing a perfect calendar, demonstrated his role as the sole link between the earthly and celestial realms. He did not just rule by divine right. He proved it year after year with mathematics and bronze, turning the silent cycles of the cosmos into the undeniable rhythm of imperial authority. That same drive for a stable calendar, so vital to imperial China, was about to transform the West in a single, dramatic act of political will. The early Roman calendar was a chaotic mess, a lunar system of just 304 days attributed to the mythical founder Romulus. It was so profoundly out of step with the solar year that it required constant, frantic adjustments by the pontifices, the state priests. These corrections were not merely scientific. They were deeply political. A powerful official could quietly extend his term in office by persuading the priests to add extra days or even months to the year. Time itself was a tool for manipulating power, and by the 1st century before the Common Era, the entire system had broken down. The Roman calendar was a staggering 3 months out of sync with the actual seasons. Winter festivals were being celebrated in what should have been autumn, and the entire rhythm of civic and agricultural life was descending into farce. Into this temporal chaos stepped Julius Caesar. Fresh from his campaigns in Egypt, he had seen the superior, stable solar calendar used in Alexandria. He returned to Rome determined to impose rational order on his republic's time. In 46 before the Common Era, acting on the expert advice of the Alexandrian astronomer Sosigenes, Caesar initiated the most radical calendar reform in Roman history. He declared that year, known as the Year of Confusion, would be 445 days long, a brutal but necessary reset to wrench Rome back into alignment with the sun. From that point forward, the new Julian calendar would follow a solar year of 365 days, with a single leap day added every 4 years to account for the extra quarter day. This was the birth of the leap year. The months were reorganized into the familiar lengths we know today, and in a fit of undeniable vanity, the Senate renamed the month quintilis to July in his honor. This was more than an administrative update. It was a triumph of empirical science over tradition and superstition. The Julian calendar standardized time across the vast expanse of the Roman Empire, creating a unified temporal framework that enabled everything from the precise scheduling of military campaigns to the reliable collection of taxes from distant provinces. It was a tool of empire as powerful as any legion, binding millions of people to a single Roman rhythm. This calendar was so effective, so perfectly engineered, that it would govern the Western world for over 1,600 years. Yet even Caesar's brilliant solution was not quite perfect. That tiny fractional day it was designed to capture was ever so slightly off, an almost invisible flaw that would, over the slow march of centuries, accumulate into a problem demanding another great reform. The relentless river of time was not just measured by gears and shadows, but pondered in the quiet of ancient academies. For the great philosophers, its true nature was the ultimate riddle. In Greece, Heraclitus gazed at a flowing stream and declared you could never step into the same river twice. For him, time was this very essence of perpetual flux, a universe where everything was in a state of ceaseless becoming. Nothing was permanent, and to resist this flow was to misunderstand reality itself. Plato, looking at the same cosmos, saw a different truth. He envisioned time as a moving image of eternity, a beautiful but imperfect copy crafted by a divine demiurge to impose mathematical order onto the primordial chaos. The perfect, timeless realm of forms was the true reality, and our experience of time was merely its shadow, playing out on the cave wall of existence. Then came Aristotle, who grounded the debate in the physical world. He defined time not as a thing in itself, but as the number of change in respect of before and after. Time, for him, was a measurement of motion, an abstract count that only existed because we observe events unfolding in a sequence. It was a relational property of the universe, inseparable from the movement of the heavens and the decay of earthly things. These were not abstract thought experiments. A society's fundamental belief about time directly shaped its most practical creations. The Maya and the ancient Hindus, who saw time as a vast, repeating wheel of cosmic ages, constructed intricate cyclical calendars. Their goal was not to mark a linear march into the future, but to align with the sacred rhythm of eternal return, to find their proper place within the great cycle. In contrast, the later Romans and the Jewish tradition, influenced by a sense of historical destiny and divine covenant, began to see time as a line. This linear perspective gave rise to detailed historical chronologies, annals of kings and prophets, a narrative of progress or redemption stretching from a singular creation toward a final culmination. The very act of building a sundial or a water clock forced humanity to confront the most profound questions. Are we measuring a fundamental property of the cosmos, a real river in which we are all carried along? Or is time merely a magnificent construct of the human mind, a story we tell ourselves to make sense of the bewildering cascade of moments? The ancient debates between the river of Heraclitus and the eternal forms of Plato did not end in their time. They echo now in the heart of modern physics, in the strange warping of space-time, and in the quantum questions about whether time itself is fundamental or emergent. The way we choose to count our hours is still, in the end, a reflection of what we believe time to be. But this knowledge was never just about the stars. The real power of measuring time unfolded here on the ground, in the fields and the city squares. For the earliest farmers, a reliable calendar was not an abstract concept. It was survival, knowing the precise week to sow seeds or the exact day to expect the life-giving rains determined whether a community would eat or starve. This shared agricultural rhythm, dictated by celestial clocks, bound villages together in a common purpose. Their labor was synchronized with the cosmos itself. Yet this power to define the seasons soon became a tool of authority. In the great river civilizations of Egypt and Mesopotamia, the pharaohs and priest kings did not simply observe the calendar. They controlled it, the declaration of the new year, the scheduling of religious festivals that drew thousands, and even the dates for collecting taxes from a dispersed population, all flowed from their monopoly on time. This was a profound form of social control. By being the sole source of temporal order, the ruler positioned himself as the indispensable link between the people and the gods. He did not just command armies, he commanded the very rhythm of life. This authority was made stone-cold real through colossal projects. The raising of a giant obelisk to cast its shadow across a royal plaza, or the centuries-long labor to align Stonehenge, were not just scientific endeavors. They were spectacular demonstrations of power, to mobilize thousands of workers for generations, to feed and house them, all to build a permanent clock, proved a ruler's ability to organize society on a breathtaking scale. The monument itself was a ticking symbol of his reign. As towns swelled into cities, this shared sense of time moved from the seasonal to the daily. In the bustling Greek agora, a public sundial allowed merchants to agree on meeting times. In the Roman Forum, a water clock could time legal speeches, ensuring each citizen received a fair hearing. For the first time, the day itself was divided into a communal resource, a schedule that coordinated the work of artisans, the business of merchants, and the rituals of priests. This shared temporal order was the invisible framework that made complex urban life possible. It even enabled empires to stretch their reach. A general could plan a military campaign months in advance, coordinating the movements of legions and supply lines across continents. A merchant could confidently send a ship across the Mediterranean, trusting in the seasonal knowledge of winds and currents that the calendar provided. The simple act of counting days had woven an invisible net connecting farmer to pharaoh and village to empire. It was this fabric of shared time, more than any law or wall, that truly held the ancient world together. The very ideas that measured the cosmos were carried on the same winds that filled the sails of merchant ships and the dust clouds of marching armies. Ancient timekeeping was never a solitary invention, but a brilliant mosaic pieced together across continents. When Alexander the Great carved his empire from Greece to the Indus River, his campaigns did more than redraw maps. They became a conduit for knowledge, carrying Greek astronomical theories and geometrical methods deep into the heart of Persia and India. Local scholars absorbed these foreign concepts, debated them, and wove them into their own rich traditions of celestial observation. This was not a one-way street. Centuries later, during the flourishing Islamic Golden Age, a massive intellectual project began in the great centers of Baghdad and Damascus. Caliphs sponsored houses of wisdom where teams of scholars tirelessly translated the works of Greek thinkers like Ptolemy, alongside texts from Persian and Indian sages. They did not merely copy these scrolls, they challenged them, corrected them, and synthesized them into something entirely new. From this cultural crossroads emerged breathtaking advancements in trigonometry, more precise solar year calculations, and incredibly complex water clocks and geared mechanisms. The astrolabe, a portable device that could solve astronomical problems and tell time, was perfected in these workshops, becoming the smartphone of the medieval world for navigators and astronomers. This river of knowledge eventually found its way back to a Europe emerging from its dark ages. The gateway was Al-Andalus, Islamic Spain, where cities like Cordoba became dazzling hubs of learning. Through the slow, patient work of translators in Toledo and other cities, this preserved and enhanced classical knowledge, now filtered through centuries of Islamic scholarship, began to seep into European monasteries and universities. Meanwhile, along the sprawling Silk Road, another exchange was quietly taking place. Caravans carried more than silk and spices. They transported calendar systems and observational techniques between the imperial astronomers of China and the mathematicians of India and the Middle East. A Chinese method for predicting eclipses might influence a Persian scholar, while Indian numerical concepts, including the revolutionary idea of zero, transformed mathematical astronomy everywhere they spread. The Greek concept of the equinoctial hour, that radical idea of 24 equal periods, did not conquer the world by itself. It was adopted and championed by Islamic astronomers who found it essential for scheduling their 5 daily prayers at precise, fixed times, and from there it was carried into Europe, where it would later become the bedrock of mechanical timekeeping. This vast, interconnected web reveals a profound truth. The history of time is a history of conversation. It is the story of human curiosity refusing to be bounded by desert or sea, driven by a shared, practical need to comprehend the rhythm of the universe. Every gear in a modern clock, every line on a digital calendar, is the heir to this timeless global collaboration. The brilliant gears of the Antikythera Mechanism are a stunning exception, a single survivor from what was likely a vast ocean of lost technology. For every one of these devices that emerges from the earth or the sea, countless others have vanished without a trace. We read in ancient texts about the magnificent water-driven clock tower built by Su Song in 11th century China, a marvel over 30 feet tall that charted the stars and told the time with a mechanical escapement. Yet no complete example of such a clock exists today. The knowledge to create these masterpieces was not stored in public libraries. It resided in the hands of a few master craftsmen, often bound by oath to secretive guilds or employed exclusively within a royal workshop. This delicate thread of expertise could be severed in an instant by a single invasion, a palace fire, or the collapse of a dynasty. The legendary Library of Alexandria, with its countless scrolls gathering the technical knowledge of the ancient world, went up in flames, and with it, entire schools of thought and manuals of engineering were likely lost forever. The historical record is full of these haunting silences. How many other mechanical wonders, perhaps even more complex than the Antikythera device, were melted down for their bronze or left to rot in forgotten storerooms? The work of piecing this puzzle back together falls to archaeologists and historians, who must become detectives of the incomplete, a single, corroded gear pulled from a Mediterranean shipwreck. A passing description of an automated theater in a faded Greek manuscript, the precise astronomical alignment of a temple foundation that nobody had noticed for centuries. Each fragment is a clue. These scattered pieces force us to constantly rewrite our understanding of the past, revealing that the technological sophistication of ancient civilizations was often far greater than we ever presumed. The gaps in our knowledge are not empty spaces. They are invitations challenging us to keep looking, to keep questioning what we think we know about the ingenuity of those who came before us. The relentless turning of the celestial wheel demanded more than just observation. It required a story. In nearly every ancient culture, the cold mathematics of timekeeping were woven into the warm, living tapestry of mythology. The Egyptians did not see the sun as a simple ball of fire. It was the god Ra sailing his golden bark across the sky each day, only to face a perilous journey through the 12 hours of the underworld each night to be reborn at dawn. This was not mere fantasy. It was a narrative that made the terrifying darkness comprehensible, transforming the daily disappearance of the sun into a divine drama of death and resurrection that everyone participated in. The Maya believed time itself was a sacred burden carried on the backs of deities. Each day and each cycle had its own divine patron, its own unique spiritual energy. The end of a major calendar cycle, like the completion of a backton, was not just a date. It was a moment of cosmic fragility when the world faced potential destruction or glorious renewal, depending on the will of the gods. This belief infused their elaborate calendar rituals with an urgent life or death significance. Far to the north, the Norse myth spoke of Ragnarok, a cataclysmic end of the world where even the gods would perish, only for the earth to rise again, green and fertile from the sea, and a new generation of gods to begin the cycle anew. This concept of a cyclical apocalypse provided a framework for understanding decay and rebirth on a grand, cosmic scale. These mythic cycles were not separate from the calendars people used. They were their very foundation. The Roman calendar was packed with festivals dedicated to gods like Janus and Saturn, whose stories explained the turning of the year and the hope for abundance. To celebrate a god's feast day was to actively participate in their story, to help ensure the sun would keep moving or the harvest would return. This fusion of measurement and mythology was a profound psychological tool. The abstract, relentless passage of time, with its inevitable conclusion in personal death, could be a source of deep anxiety. But by placing human lives inside a grand, divine narrative of endless cycles and sacred journeys, that fear was transformed. An individual's life, however brief, became a meaningful part of a story that had no end. The daily grind, the changing seasons, even the fall of empires, were all just acts in a play written by the gods. This deep, human need to find meaning in measurement reminds us that every clock we build and every calendar we mark is, in its own way, a search for our place in a story much larger than ourselves. Even the most brilliant sundial cast no shadow on a moonless night. A water clock's steady drip would slow to a crawl on a frigid winter evening as the water thickened near freezing. These were not mere inconveniences but fundamental boundaries to ancient precision. The tools they built were masterpieces of their environment, yet they were prisoners of it too. A sundial required a visible sun. A water clock's accuracy was at the mercy of temperature, which changed the water's viscosity, and sediment, which could slowly clog its carefully drilled hole. The pressure of the water itself was a variable, as the flow from a main reservoir would subtly decrease as its level dropped, making the final hours of its cycle slightly longer than the first. For tracking the turning of the seasons or the hour of a religious ritual, this was often enough. Most daily life did not demand precision down to the minute. Knowing the time within a quarter of an hour was, for the vast majority of people, perfectly sufficient. The greater challenge lay in the longer cycles. A lunar calendar, beautiful in its symmetry, would inevitably drift from the solar year, forcing societies to periodically insert an extra month. This intercalation was a complex art, and the decision of when to add that month was sometimes as much a political or religious calculation as an astronomical one. Tradition could be a powerful anchor, resisting the tide of rational improvement. The chaotic state of the Roman calendar before Julius Caesar's reform is a perfect example. The system was known to be broken, a public absurdity, yet the political and religious establishment resisted fixing it for generations, preferring the flawed devil they knew to the rational order proposed by outsiders. Access to time was also a matter of class. The knowledge of how to read a complex water clock, how to calculate an equinox, or how to interpret an eclipse was often guarded by a privileged few. Priests, royal astronomers, and scribes held this power, using it to reinforce their authority and connection to the divine. For the farmer in his field or the potter at her wheel, time was a more immediate experience marked by the sun's height, the crow of a rooster, or the simple weariness of the body. These limitations are not failures of intellect. They are profound reminders that technology does not evolve in a vacuum. It answers the specific questions a society is asking, using the materials and concepts it has at hand. The ancient world did not need railway timetables synchronized to the second. It needed to know when to plant, when to celebrate the gods, and when the sun would return after the long winter. Their clocks, for all their earthly constraints, solved these problems with an elegance we are only now coming to fully appreciate. That Babylonian base 60 system is the silent architecture of your entire day. Every time you glance at a clock, you are reading a 3,000-year-old mathematical decision. The choice of 60 was one of genius, for it can be cleanly divided by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This made it the perfect foundation for merchants dividing goods, astronomers calculating angles, and generations of people simply trying to split an hour into manageable parts. Our 24-hour day, 60-minute hour, and 60-second minute are all built upon this ancient numerical bedrock. Even the names of our months are Roman echoes. July and August honor Julius and Augustus Caesar, while September, October, November, and December cling to their old Latin numerical names, forever marking the 7th through 10th months in a calendar that long ago shifted its start. The 7-day week itself is a Babylonian invention, each day originally assigned to one of the 7 celestial bodies they could see moving against the fixed stars. The Sun, the Moon, Mars, Mercury, Jupiter, Venus, and Saturn each governed an hour of the day, and the day itself was named for its first hour. This poetic system was adopted by the Romans and later woven into the fabric of Abrahamic traditions, sanctifying a cycle of work and rest that now structures life across the globe. Our own Gregorian calendar is not a modern invention. It is a direct and refined descendant of Julius Caesar's Julian reform, a correction so effective its basic framework has endured for over 2 millennia. This legacy is not confined to names and numbers. The very drive that pushes us to build atomic clocks, which measure time by the unwavering vibration of cesium atoms, is the same human impulse that led a Bronze Age artisan to inlay the Pleiades on a golden disk. It is the endless quest to tether our fleeting human activities to something constant and cosmic, to find a rhythm more reliable than our own heartbeat. We still look to the heavens for our most fundamental standard. The precise orientation of a modern building or the launch window for a spacecraft relies on astronomical calculations that would feel deeply familiar to the builders of Stonehenge. The core needs that drove the ancients to raise stone circles and cast bronze gears are identical to the needs that fill our world with smartphones and satellite navigation. We still need to schedule our lives, to plan for the future, and to find meaning in the cycles of our own existence. By tracing the line from a shadow on a sundial to the pulse of an atom, we see a continuous story of human curiosity and ingenuity. This long and interconnected history reminds us that every second we count is a gift from the past, a measurement of a journey that began when the first human looked up at the stars and wondered when. The sundial and the water clock represent more than just tools. They embody 2 fundamentally different ways of seeing our place in the cosmos. Western traditions, shaped by Greek philosophy and Roman administration, came to view time as a straight line, a sequence of unique events marching from a past creation toward a future destiny. This linear perspective was practical and powerful. It fueled the desire to chronicle history, to measure precise intervals for law and commerce, and to build mechanisms like the Antikythera device that modeled the heavens as a predictable machine. Time was a resource to be managed, a force to be harnessed for human progress and civic order. The relentless tick of a water clock in a Roman courtroom was the sound of this worldview in action, quantifying moments for the purpose of human justice. Meanwhile, on the other side of the world, a different understanding had taken root. In China, time was not a line but a wheel, an expression of cosmic harmony. The emperor's mandate to rule was proven by the flawless accuracy of the state calendar, a unisolar system that synchronized human society with the rhythms of heaven. A mistake in predicting a season or an eclipse was not a mere scientific error. It was a cosmic crisis, a sign that the connection between the earthly and celestial realms had been broken. The colossal water-driven clock towers and imperial observatories were not built to conquer time, but to meticulously align with it, ensuring the empire remained in its proper place within the universal order. This philosophical chasm is even wider in ancient India, where astronomers calculated the solar year with astonishing precision while their philosophers contemplated the Mahayugas, cycles of creation and dissolution spanning millions of years. Here, the brief flash of a human life was set against a backdrop of almost unimaginable vastness, a rhythmic pulse of cosmic breath that made linear progress seem almost trivial. One culture sought to master time for human use, carving it into ever smaller, manageable pieces. The other sought to understand its flow, to find a sacred rhythm within its endless turnings. This was not a contest of superiority, but a reflection of deep cultural priorities. The West gave us the precise hour, the historical timeline, and the mechanical clock. The East gave us the concept of eternal return, the state calendar as a tool of cosmic balance, and a spiritual acceptance of time's cyclical nature. Your own relationship with time, whether you see your day as a checklist to be completed or a cycle to be experienced, is still touched by this ancient, global conversation. Even the most brilliant artifacts leave a trail of unanswered questions. The Antikythera Mechanism stands as a lonely peak of ancient engineering, but how did its creators achieve such sophistication? And why did that knowledge vanish without a trace for over a millennium? Was it a unique masterpiece from a single genius, or was it part of a broader tradition of complex machinery, all of which were eventually melted down for scrap or lost to decay? Its very existence suggests a hidden chapter in the history of technology, one we have only glimpsed. Similar mysteries stretch across the globe. High in the arid plains of Peru, the vast Nazca lines etch giant geometric patterns and animal figures into the desert floor. While some theories suggest they were ritual pathways, others propose they functioned as a colossal calendar, their immense spider, monkey, and hummingbird shapes aligning with celestial events like the solstice sun or the rising of the Pleiades. Could these geoglyphs be a sprawling, sacred almanac written on the earth itself, meant to be read by the gods above? We simply do not know for certain. The true depth of ancient astronomical wisdom remains just out of reach. The precise methods of the Druids at Stonehenge are lost to us, their oral traditions silenced. How did Polynesian navigators, traversing the vast emptiness of the Pacific, use the star paths, ocean swells, and even the flight patterns of birds to measure time and distance with such stunning accuracy? Their knowledge was a living, embodied science passed down through generations without a written manual. Today, new eyes are scanning the planet, offering fresh clues. Technologies like LiDAR, which uses lasers to see through dense jungle canopy, and advanced satellite imaging are revealing previously hidden structures, entire cities, ceremonial centers, and earthworks whose alignments we are only beginning to analyze. Each new discovery has the potential to rewrite our understanding of how ancient civilizations perceived and mapped the heavens. These are not dead ends in our historical investigation. They are open invitations. The silent stones and corroded gears are still speaking, challenging us to look deeper and think differently. The exploration of ancient time is a living, breathing field of study, reminding us that the past still holds profound secrets, waiting for the right question, the right technology, or the right curious mind to bring them into the light. Our journey ends not with a final tick, but with a profound echo. The story of ancient time is a testament to incredible human ingenuity, a force driven by our most fundamental needs. We sought to survive, to predict the floods and the harvests. We yearned to worship, to align our rituals with the sacred dance of the heavens. And above all, we struggled to understand our own fleeting place within the vast cosmos. From the silent, waiting stones of Stonehenge to the intricate, whirring gears of the Antikythera Mechanism, from the lunar cycles of Babylon to the solar precision of Egypt, we see a universal impulse. It is the desire to capture the river of moments and impose a human order upon its flow. These systems were far more than practical tools for farming or governance. They were profound expressions of philosophy carved in stone, art cast in bronze, and power inscribed on the calendar. They were woven into the very spiritual and cultural fabric of every society that created them. This long and interconnected history reminds us that our modern world, with its atomic clocks and digital schedules, rests upon a foundation built over millennia. It is a foundation of relentless observation, of brilliant innovation, and of a timeless conversation that crossed deserts and oceans. The next time you glance at your watch to check the time, pause for a single second. Remember the long and fascinating journey that led to that number on the screen. Consider how the ancient quest to measure the cosmos continues to silently shape our daily lives, our science, and our